So yeah, alphaXiv began approximately a year ago, and the goal was just to bring researchers together. It started as like a commenting platform on archive papers, and the thinking being, everyone is reading these papers in archive these days, and there should be a place to kind of have discussions. And since then, it's kind of evolved into a lot more. We've introduced a lot more tools to help people better discover, read, and understand research papers, and also launch these communities as a way of like bringing people together in a specific field or area of interest. So we have our AI for Science community that's been really strong for the last couple of months, and recently we've been honored to have Vals AI kickstart this AI evals community. And yeah, it's our first talk. Super honored to have them and Shashwat as well. So I'll let Ryan and Nikhil take it from here.
Ryan, are you able to unmute yourself?
Yeah, sorry, it seemed like I did not have permission for a bit, but thanks for that, Raj. Yeah, I can say a few words on Vals, and then I'm sure we're all excited to hear from Shashwat. But I'm one of the co-founders of this company, Vals, and we, as you can see on our public benchmarking site, we study how well language models do real-world tasks. It's quite adjacent to some of what I think Shashwat will talk about, but we observe this problem about having these academic benchmarks, which are sometimes measuring not the right things, and so figured it would be useful to build our own proprietary benchmarks on real-world tasks. And there's a lot more still to do, but we've seen a shifting tide even over the last year, where now Sonnet 4.5 came out, and they're relying on some of our benchmarks as opposed to those contrived academic-focused benchmarks. So anyway, we figured it'd be useful to gather some of the people we really respect and look to in the academic community, and we're excited to collaborate with alphaXiv to do that. Nikhil, any other last words you want to say as well?
Yeah, no, it's super exciting. We're excited to have Shashwat. He's been working a lot on long horizon evals and thinking about MCQ tasks versus answer matching. And we're excited to have him. One thing I'll add is if you have questions, please use the Q&A tab at the bottom instead of chat. That way we can organize the Q&A a bit more, and we'll have a period in between where we'll take questions.
Yep.
Yeah.
And this meeting is being recorded, so we'll post that in the community as well. And I'm sure that we'll be tweeting it and sending in the Luma following the event as well. So yeah. Sorry, Shashwat, go ahead.
Hi everyone, I'm Shashwat. I am doing a PhD focused on like benchmarking and evaluations, which fits in quite well with the interest of this like AI evals community. And I'm excited to like talk a bit about my work, and towards the end also have like some sort of open-ended discussion on where I think evals are lacking, where we are going, and so on. Should I get started with my presentation? Yeah, sounds good. The title of the presentation is Measuring AI Progress Requires Rethinking Evaluations, which is a bit of a bold claim, but I think hopefully I will be able to convince you why I think like traditional benchmarking has like a couple of problems which require like significant shifts in how we evaluate models. So, but before we get into all of this, I think like first, just to like motivate the problem, I think we are everyone who's tracking AI progress these days is confused, and this is because there's like all sorts of like conflicting viewpoints coming in. Where like in the slide, I just have like a bunch of screenshots of like contradictory pieces of evidence coming from different people. So, for example, on one hand, you have like people like Gary Marcus saying that we've reached like some sort of point of diminishing returns with LLMs where improvements are slowing down. On the other side, we have like the meter task length chart. I don't know if you guys have come across this, but they kind of showed that models are able to complete longer and longer tasks in every subsequent release. And then some people think that GPT-5 was like a point of like where models kind of have started slowing down. We don't really feel the difference anymore, whereas other people who, let's say, use the model on Cursor think that it's mind-blowing. So overall, I think there's like some sort of like increasing confusion in what is going on with model evaluations. Whereas like, let's say between 2022 to 2020, 2024, early 2025, it was kind of clear that models were improving significantly. Like you could feel the difference, whereas now like it seems like you can feel the difference less and less. So I'm going to talk a bit about how this affects, like how evaluations shape this perception, and also how sometimes they can shape it in like a misleading way. So but the first point really with like what evaluations really try to solve fundamentally is like all of these are like viewpoints people have. These are like opinions, and they're not really like quantitative measurements sometimes. And evals try to like bridge this gap between people who are bullish on AI progress versus people who are bearish on AI progress, and think like models are good versus bad and so on. So evals really try to paint more of a scientific picture on where we really are in terms of different capabilities. And that's really the goal that I will also try to have for my talk, where I will try to bridge these like conflicting viewpoints through like some of my work. So I think one thing to realize, which is quite important, is that in machine learning, evaluations really guide AI progress. For example, in like 2005 to 2015, 2020, we had like ImageNet guiding most of AI progress. People were hill climbing ImageNet, trying to improve models by testing on ImageNet. And then we had like MMLU, which took up a lot of mindshare after that until like, let's say 2024. Every major new model release was essentially the flagship headline used to be its MMLU score. And now we have some sort of shift towards, let's say, SWE-bench, which again focuses on a very specific task of like whether models can solve coding issues. So based on what the current popular evaluation is, I think companies also like shift their priorities a bit towards that, towards like hill climbing a particular benchmark. And for a researcher, having some sort of evaluation to guide whether they're actually making progress is really important. And like another thing that is becoming more and more clear recently is that honestly, like any task that you can reliably evaluate AI performance on, you can optimize for. And this like in in the traditional sense, this was in like back in the ImageNet days, you had some sort of graduate student descent where you had like you told like a lot of PhD students that, hey, like just go and make progress on ImageNet. And then like people were coming up with like all sorts of small improvements, which eventually compounded into like over like a decade a very large improvement on ImageNet. And these days you can even do some of this with just like doing RL on a evaluation. Like once you have some sort of evaluation metric, you can optimize it with RL, and that is turning out to be quite successful. And obviously the bold part here is reliably, because once you if you're not reliably evaluating the capability, then once you start optimizing for it, you start optimizing maybe for the wrong things, or like where it is misaligned with like actual user experience or whatever your downstream goal is. So the first problem really like that this brings up is that, okay, for coding and math kind of domains where you can just run like a compiler or something and essentially get verifiable perfect feedback, there we can reliably evaluate things. And that's why models are like increasingly becoming excellent at code, like even to some extent superhuman at code. And uh, the big question is like, okay, coding is like a small part of what a small section of society does, but most of our daily decision making happens on like much more of these like what people call non-verifiable domains. But I mean, I don't like the term non-verifiable, because essentially everything has like some downstream reward signal. It's just sometimes harder to directly measure it. And so how do you evaluate models on like these kinds of capabilities, which you can't just execute on a compiler and get a measurement? And then the second thing is that most of machine learning has like until now focused on these short tasks. Like ImageNet was like a simple classification task. Humans can probably do image recognition in like 1 second. And then we gradually move towards more like Q&A style benchmarks like MMLU, where again you have like exam style questions based on like what the multiple choice questions we give to like, let's say, any student for a test. And we started evaluating models on these. And again, like uh, this is also not, I think, fully enough, because if you think about it, like the questions that you ask ChatGPT when you use it are like unless you're using it only for like some specific coding reasons, a lot of the questions you end up asking or the general population asks is not going to be some sort of like coding or math question which can be easily verified. And B, like it's usually going to be some open-ended question where the model gives some generative response, something like oh, like my microwave broke down. How do I fix this? I see this like weird flashing light on it. What is going wrong, and so on. So again, these kind of like any response to this is like somewhat harder to verify. You can't just like run a compiler and see if the output was correct or not. So these are the two problems that I'll mostly talk about uh, today. And as like a motivating example of so if you think about like how we do testing, even for humans, and also for language models, at least until like very recently, for these non-verifiable domains, like let's say physics questions or something, often like the questions end up being some sort of multiple choice questions. So I took like one question from MMLU Pro, which is like one of the popular benchmarks for general understanding and knowledge. And I've basically put some, like I've basically hidden the question from you and only showing you the options. And if you look at the options carefully, you will probably notice a pattern. Most of the options end with a zero. And then there is this one weird option out here, which is like quite precise. It's like 601. And I mean, I don't know about you, but growing up, whenever I was giving like these multiple choice exams, I used to do a lot of this hack or like cheat where if I didn't know how to answer a question, I mean, anyway, I was like under some sort of time pressure. I would sometimes just look at the options, see if I find some anomaly like this, and I would just pick that option. And this somewhat paid off in many cases. And indeed, like in this question from MLU, like this is like some question about physics, like measurements. I think actually this one is about chemistry, but you see that like among these options, the odd one out option is actually correct. And in fact, like people have been noticing this a bit on like some other benchmarks as well. So there was this very interesting blog post around a year back on this benchmark called Truthful QA, which is used to check how factual model outputs are. And they also kind of showed that like using this odd one out heuristic leads to like a 73% accuracy on this like 4 choice benchmark. And well, how did so the Truthful QA authors like saw this and they responded to this, and the way they responded to this was very interesting. What they did was they took their 4 choice multiple choice questions and essentially threw out 2 of the choices and made like a 2 choice version. So now this solves the odd one out problem where you can't look at the options and pick the odd one out because there are only 2 options and both of them are different from each other. And they claim this kind of like solves this issue, but actually what's, if you think about it, what's going on is like actually deeper and more interesting. So for that, maybe the first thing to do here is like actually formulate why we use multiple choice and what really are we trying to measure with question answering benchmarks. So like consider like a very simple formulation of what question answering benchmarks are. You have like some sort of question queue. You have some set of correct answers, which is illustrated here by this green box, AQ. And then you have like some candidate response R from a model or a human or whoever. And the ideal evaluation wants to check whether the response is in the set of correct answers. And the reason why this is like a set is that for any question like who is the president of the United States, uh, you could have like uh, different paraphrases of the same answer as well. So you could have Donald Trump, you could have Donald J. Trump, you could have Trump, you could have any other name you want to call him. And these are all like paraphrases, but they kind of make it difficult to do like direct string matching with like one answer string. So that's why you can't really perfectly verify this simple question as well. And basically, yeah, so the set of answers can be large, sometimes like so large that you can't even enumerate all the possible paraphrases. And multiple choice tries to fix this by essentially in the choices only including one correct answer and then keeping some wrong answers sampled from the rest of the space. And this way now only one choice is correct, so you kind of solve this problem of the answer set being having more than one element by just picking one of the correct elements. And this seems to like really mitigate this problem, but actually this is like bringing a new issue in, which is that uh, multiple choice questions measure like fundamentally a different task. What they measure is whether you can separate correct choices from a bunch of incorrect choices. So it essentially, if you think about it, becomes like a typical machine learning classification problem where you have one correct class and then you have some incorrect classes sampled, and you need to separate the correct and the incorrect classes. This is like a discriminative problem in machine learning. And this is problematic, right? Because most of the queries we ask models are like in some free-form generative format where we just ask the question, oh, I want to fix my microwave, help me. Whereas we don't say like, oh, I want to fix my microwave. Here are 4 options that I have to fix it. Can you help me pick one of these? I don't think anyone asks ChatGPT questions in multiple choice format. And really, like, what this means fundamentally is that since multiple choice makes it like a separation task between the choices, you can actually maybe even separate the choices without looking at the question sometimes. And that's kind of what we were doing with the odd one out example, where without even looking at the question, we were able to like separate the correct choice from the incorrect ones. And really, like, one thing to ask here is then how much can we push this? Like, odd one out is one type of heuristic to cheat on MCQ benchmarks, but can we push this further? And to test this, we set up like a very simple experiment where we took the Chen 3-4B model, we we removed the question and only give it like the 4 choices or 10 choices in the benchmark across like multiple popular benchmarks. And then we trained like this linear classifier on top of Chen 3 embeddings with like a 50-50 train test split. And we fit the classifier on the train set and then tested it on the test set. And this actually like gives you like a lower bound in theory on the statistical separation between the choices, which you can measure with like the total variation distance, if that uh, if that's something you're familiar with. Or in practice, obviously models might not be able to like exploit these choice only shortcuts perfectly, but to some extent they still can, and you will probably never know because we haven't solved interpretability yet. So it's somewhat of an upper bound in practice in terms of how much the models actually exploit this shortcut. And what I want to motivate here, like what we found with this experiment, was that across popular benchmarks, you can actually like answer a lot of questions without even looking at the question. So the red bar here kind of shows the accuracy you can get on the benchmark. And obviously in multiple choice, there is like some expected chance accuracy, which is demarcated in green for the different benchmarks. And there is also like this blue dashed line, which shows what the actual accuracy of the model is with just prompting, which, as you can see, sometimes can actually be lower than what you can achieve without even looking at the question for some models and some data sets. And so some of the interesting things on this plot are these are like truthful QAV2 and golden swag are essentially like 2 updated versions of popular datasets. Truthful QAV2 is of truthful QA, and golden swag was like a recent release updating Hella swag, which is like a very popular pre-training dataset. And in both of these, you can get like one thing we noticed was the choice only shortcut accuracy is actually much higher than the original version. So in trying to improve the benchmark, they actually end up worsening it in terms of the shortcuts introduced. And then another interesting thing we noticed was that again, with multiple choice questions, mostly what you have is like a question and like one correct ground truth answer. But and most of the incorrect answers are like something artificially chosen by humans or so on. And a lot of people have tried to use LLMs to like create these different choices just to save effort in terms of benchmark creation. And examples of this include MMLU Pro, which extended MMLU from 4 to 10 choices by using some sort of LLM augmentation in the choices. And then Hugging Face also had this interesting release earlier this year called Your Bench, where they essentially automatically try to create multiple choice benchmarks. And they released a variant of MMLU, which they claim is harder than the actual MMLU. And similarly, Super GPQA is supposed to be like a harder version of GPQA across domains. And in all these LLM generated or LLM augmented benchmarks, in trying to improve the benchmark using LLM augmentation, what we observe is that the number of shortcuts or the number of questions you can answer without looking at the question increases a lot. Like in Your Bench, which is completely LLM generated, it's like 61% compared to 39% in MMLU. And then the last most interesting thing maybe about this plot is this result on MMMU Pro, which is like still considered a frontier multimodal benchmark. I think the Claude 4.5 Sonnet release, or like one of the recent Claude releases, actually again reports this benchmark. And one funny thing you notice is that again, like without even showing the image or the question, you can get above 50% accuracy on this multimodal benchmark just using like a linear classifier on like a small model's embeddings. So again, like this goes to show that multiple choice is like, again, a discriminative problem, and it can be solved without looking at the question by treating it as a discriminative problem. And then in our work, we kind of like showed a way to get around this, which is like, how do you actually evaluate responses without giving any choices to the model? You just give the question to the model. So obviously, like when you get this free-form response out, one popular technique is LLM as a judge, and answer matching is like essentially a lesser known cousin of LLM as a judge, where you essentially give like a language model the LLM response, like the response that you're grading, and like a reference answer, and then you simply ask the language model, does this response match the reference answer, invariant to some sort of paraphrasing. And models are great at paraphrase detection, right? Like that's been a solved problem for quite some time now. So really the insight here is that without the reference answer, the model has to do some sort of verification, where if it doesn't know the answer itself or doesn't know how to solve the question, it can't really verify the question sometimes, the response sometimes. But then once you give it the reference answer, it just has to solve like a simpler paraphrase detection problem. And the way we kind of test this, whether like this actually aligns better with human grading, is we basically took like a bunch of MMLU Pro and GPQ Diamond questions. We took model responses across like 4 different frontier models, and then we actually sat down and manually annotated these responses and graded them using like web search, having access to all sorts of additional tools to help our grading. And essentially, if you obviously this answer matching technique only works if you have access to like a reference answer. So you need to filter out some questions where like many possible answers are correct, or like if they're vague and ambiguous and so on. So especially in like some of these popular benchmarks, we saw that they really depend on the option sometimes to like specify the question properly. So once you do all this filtering, what you observe is that um, like you can measure the alignment between the outcomes of MCQ grading, of LLM as a judge grading, which is in yellow here, and answer matching grading, which is in blue. And here I have like the interhuman agreement in green. And what you can probably see is that even Llama 4 Scout, which is like a cheap open weights model to access, achieves like nearly human level agreement on this task of answer matching, or like grading using answer matching. And also like a 4B model has like quite high alignment with human grading, whereas MCQ has like extremely low alignment with human grading. In fact, it's worse than Llama 2 7B in some sense. So it's like using Llama 2 7B as your matcher every time you use MCQ to evaluate these benchmarks. And this has like a bunch of practical implications where, for example, people are worried that GPQ Diamond is getting saturated. Like Epoch had this whole report on whether they think GPQ Diamond is saturated or not. And we kind of like, one of my co-authors like keeps releasing like these posts about new models and what they score on GPQA once you evaluate it in free form without showing the model the choices. And one thing we consistently find is that while Grok 4 and O4 Mini had like, they do seem to saturate GPQ in the MCQ format, once you don't give them the choices, the accuracies are actually much lower. So in some sense, saturation of GPQ Diamond is a mirage caused by using multiple choice questions. And also like the rankings of different models can change once you switch from multiple choice to freeform. And one last thing on this topic is just that people think that LLM as a judge, or like using LLMs to grade, is expensive. Whereas we found that actually this ended up being cheaper for us than multiple choice questions, because we found that models tend to, like when you ask models to answer a multiple choice question, they end up like blabbering and reasoning a lot about the choices. We averaged this over like 17 different models, and the options sort of like confuse them and make them produce more tokens, which increases the cost of evaluation, because in the end the cost of evaluation is dominated by the output tokens of the model trying to respond to the question. So I will take some questions here from the chat as well. But one thing before I close out this part of the presentation is just that in the end, like this doesn't solve all of generative evaluation. Like answer matching essentially makes it simpler to verify once you have a reference answer, and it works well. Like we've shown it works well on like these short answer questions, which are there in like popular benchmarks like MLU Pro and GPQ Diamond, where the final answer is quite short. But it doesn't work obviously if there are like many different answers possible, if there's like subjectivity. And also you can't really take like any MCQ benchmark and just throw out the choices, because the benchmarks are sort of sometimes the questions will be like, which of the following is best? And there, if you don't have the choices, you can't really use that question anymore. So you have to do some sort of filtering before you convert the MCQ benchmark to generative evaluation. So I'll take some questions here before I go to the next part.
Yeah, I see one question from Jacob. He asks, can we interpret the blue minus red as a quality metric for the benchmark? I'm guessing this refers to the shortcut block that you had.
Yeah, the blue minus red as quality. Yeah, so I mean, to some extent, yes, that is true in the sense that, so I guess by blue you mean like this prompted accuracy here. Uh, I won't say, like, there is a problem with interpreting this as a quality metric, which is that it really depends on what accuracy the models actually get on this benchmark. So for example, GPQ is hard, and GPQ is actually a high quality benchmark because if you look at their, like, this is like a old paper and like an old data set, but they took a lot of care to make sure that their choices did not lead to these shortcuts. In fact, they filtered in the same way that we find these shortcuts. So this is a high quality benchmark because the red and green are not very different. But the blue could be low just because like it's a hard benchmark. So the hardness of the benchmark would confound such a metric.
Cool. I guess I had a question. You had this plot of the GPQA diamond accuracy on the left, and then the same without multiple choice on the right. I'm wondering if there's evidence that these are these correlated at all, or like is there a case where it's actually not even correlated?
Oh, I think they are quite correlated in the sense that, right now, what I'm showing you is like a screenshot of just the top models. But we all, like, if you look at the full plot, obviously, like completely weak models, like smaller models, would definitely end up worse on both MCQ and generative. So they are quite correlated if you look at all the models available out there. But then it starts to become less clear when you focus on, let's say, just the top or like similar capability models.
Got it. There's a couple more questions in the chat. One of them is most real world tasks don't have reference answers and are judged more generally on vibe. Any thoughts on how you can evaluate that?
I think that's a great open-ended question, and I'll come to this maybe. It's more of a discussion question that we can talk a bit about towards the end of my slides, because I think this is one of the open questions I also list in my list of open questions.
And then Sai Chandu asks, when we use LLM for judging, should it be a reasoning LLM?
That's a good question. So I guess like it depends on the task. So one of the benchmarks that uses answer matching is also humanities last exam. And the reason they use like a reasoning model here for answer matching essentially is that uh, the questions are sometimes of like the form of like, let's say, some mathematical equation. And then the final answer is also like some mathematical answer. And sometimes even to do answer matching, like you could have like the reference answer could be some weird formula combining like different uh, trigonometry variables. And sometimes to even do this simplification to check if the two answers are functionally equivalent, you need some sort of reasoning and simplification to show that these two equations are equivalent. So it, I guess, really depends on what kind of task you're using. For a lot of tasks, you can get away without using a reasoning model, which is, I think, true for the tasks that I was talking about, like MValue Pro and GPQ Diamond. But then if your answer could be like some more complicated thing which requires where equivalence is harder to test, then you would probably want to use a reasoning model.
Makes sense. And then last question before we move on. For freeform that is not MCQ questions, what are other common methods other than using LLM as a judge?
Again, great question. And I think the only two methods that I've seen is like, I mean, so the first thing I want to motivate is when people say LLM as a judge, this could mean like a lot of different things. So answer matching was one of the things where we literally just gave the LLM judge the reference answer and said, does this match, like this, does this response match the reference answer or not? Then you could have like, basically you want to ground your LLM judge in whatever way is possible. And within LLM as judge, you could have like fine-tuned LLM as a judge, or you could give it a rubric which depending on the quality of your rubric makes the task easier or harder to grade. So it's kind of like saying, is there any alternative to humans for grading? And the answer really is like probably not. Like you need like humans or LM as a judge, as a proxy of humans, but then you can make it easier for the grader in different ways.
Cool. Yeah, maybe we can move on. I do see a couple more questions, but perhaps we can take this in the.
Yeah, makes sense. Yeah, so that was like the first part. But then one thing like I think is also being pointed out from these questions is that we're still like, even with answer matching, where like which requires a reference answer, we're still stuck in this traditional QA way of evaluating things. And obviously like all traditional ML benchmarks were like classification or question answering benchmarks for language and so on. But again, like we've kind of seen that this paradigm is somewhat saturating, and you need to create like extremely hard questions to trip the models in different ways. And one of the things we observed over the last year was we started shifting from like very simple question answering benchmarks to more like coding benchmarks, where the model in the end is obviously producing some code files which you could consider an answer, but then these are like longer in nature. Like these are long tasks to some extent, where like traditional QA tasks didn't require you to like think for more than a few minutes. These like sweep bench issues would take like something in the order of like maybe an hour or more for a human to solve. And in the limit, obviously we want agents to solve like even longer tasks. We want agents that can do like an entire project. So again, if you put these things on like a simple axis, then ImageNet was kind of like a 1 second task for humans. MMLU is like a few minutes. Sweetbench is like a few hours maybe, or like even the IMO problems that models are excellent at solving. IMO is like the Math Olympiad. Uh, so, but the end goal is kind of like models, let's say, autonomously solving an entire project, right? I give it a project spec and it just goes and completes the project for me with some test time compute. And typically projects are in the order of like hundreds of days uh, in like human time at least. And essentially what our benchmarks have been measuring is like slowly making progress from 1 second to a few hours. But there's still a long way to go in terms of like the entire project. And obviously, this is like a good point where you introduce what Jan LeCun has used as an argument for LLMs being doomed, which is that as you make a task longer, the probability of like an erroneous token being produced in an autoregressive model like increases exponentially. And this has been used to argue that autoregressive models like are not going to make it. They're not the future. But then I want to like talk a bit about our recent work, which kind of flips this argument on its head. And what we really show is that under the same model where you assume like some like constant error rate with every token, and like you again assume there is no self-correction, which is that the model, once it produces an erroneous token, it can't really correct itself. Both of these assumptions are not true essentially, but then you can use them for theoretical modeling. Under like these simple assumptions, what you can show is that small improvements in like each step essentially compound to like exponential or even sometimes faster than exponential growth in the length of task that a model can complete. And when I say this, I mean like obviously very specific things, where when I say the length of task a model can complete, or it's like horizon length, I mean the length of task or like the number of steps it can perform above a certain success rate S, which could be like in most of the cases here we take like 50%. And in this plot we kind of plot different values of S and show how essentially after you reach like 80% step accuracy, every small gain in step accuracy or like accuracy on a short task means like essentially the model can complete much longer tasks in terms of its horizon length. And one question you might ask is, oh, why do I care about this like long horizon length behavior? And the simple answer to that is like the economic value of models probably will come from the length of tasks they can do, because again, this is how we compensate human labor, right? We pay freelancers by the hour. We pay like even like any employee by like on a monthly basis. So there is like some crucial component of time, and if a model can automate 1 month of work, I would probably be willing to pay $2,000 for such a model subscription plan. And yeah, so essentially like that's why in some sense like most of the benchmarks being like these short tasks start to give you like some sort of illusion of model progress slowing. So for example, this plot was quite viral, where like when Anthropic released Claude Opus 4.1, they made like a very small improvement in SweBench performance compared to Opus 4, which came out a few months before that. And people were like, okay, AI progress is slowing down. But really, what I want to motivate is that SweBench is still like one issue, right? If you compound this over like what a software engineer does, maybe a software engineer solves like 100 issues over a month. And once you start compounding this small 2% gain, it would actually mean that your success rate over 100 issues is like much, much larger than what your success rate was here. And that's why like the meter plot, I think, is like something that a lot of frontier lab people talk about, because I think they have a good sense of the fact that what really matters now is the length of task that the model can do, and not the accuracy on like short tasks. And indeed, like meter did find that Opus 4.1 like does 30% longer tasks than Opus 4, which feels much larger than like the 2% SweBench improvement. And what I want to motivate here a bit is like some of the experiments we did in like the paper we had, which was called like the illusion of diminishing returns, just to show that how this long horizon performance can change even with model scale and test time compute. So for this, maybe I'll just motivate, like, let's say you have like a flight booking agent, right? So what the agent does is that it gets some search results, and then based on them, it like applies a bunch of checks, like checking the timings, the rewards available, the discount points available for the flight, and then overall, like combining all of these user preferences, the agent will take some action and decide on picking one flight. And mostly, what I want to motivate here is that in terms of like flight agents, what they're probably very good at is like you tell them they want, like you tell GPT-5 you want to do this task, it will give you this plan for how to do the task quite well. But then each step here, like verifying the timings or applying discounts, all of these steps require execution of some sort, which is like a bunch of clicks. And essentially, what I want to motivate is that these clicks are actually what makes tasks really hard sometimes. Because when we say that agents can't do long horizon tasks, one of the main things that people think of is, oh, models can't plan, they can't reason, and so on. Whereas actually, like the hard part sometimes is just the execution of the plan, even when the plan is very simple. And this is actually what we wanted to measure. Like we wanted to measure how well can a model execute like a given plan, or like a well laid out plan. And one way we used to model it is like essentially execution of any plan requires like some level of retrieving relevant information, like retrieving the flight timings, and then composing it with like some state that you're maintaining of like, okay, do I want to pick this flight or not? Based on each piece of information, I will update my belief, and then finally make my final decision. And again, in math derivations, you'll like, let's say, retrieve Pythagoras theorem, which is like a known relation, and then compose it with like your current equation to like transform the equation and move towards the final state. So we use like some sort of like synthetic task modeled after this way of retrieving and composing to isolate execution capabilities of models, to kind of show that even if a model has perfect world knowledge, it has like perfect, like it is given the plan, even then like execution can be really hard. And this, I think, is a bit counterintuitive, because again, you have papers like the illusion of thinking saying that models can't reason because they can't solve longer tasks. What we want to motivate is that in longer tasks, the hard part sometimes is just correctly executing the long task, even when you know exactly how to solve it. And to some extent, this is like true for most of these results that have shown that models fail on longer tasks. So to do this, what we do is we try to basically make the simplest task possible, where models, like in a single step, models have like 100% accuracy. So we take this task where we give the model like a dictionary with like some keys and some values, and then in each turn we essentially ask the model to add up the values of some of the keys. So here, like we give it like apple and grape, and we say that add the values associated with apple and grape, and the model just has to maintain like a running sum in this task. So the goal is just maintaining this running sum, which is a simple task. We've given all the knowledge to the model, which is like the dictionary provided in context. The plan, there is no planning involved, because we are just providing the keys or like the decisions in some sense to the model. And the model just has to execute this, like retrieving the correct value and then applying it and summing it and so on. So the reason why we chose this synthetic task was this allows us to very precisely control the number of turns, the number of steps, and the complexity per turn and so on, because the number of turns is just the number of queries you make of like different sets of keys. The turn complexity is essentially the number of keys you give in one turn, and one step is just adding one key's value. So this is not possible in like a lot of realistic agent benchmarks or like reasoning benchmarks, because given like a flight booking task, right, I don't know how many steps my model will take, and this can vary across models and so on. Whereas here we have like a good notion of what one step is, which allows us like some clean analysis on how execution trends across number of steps. So essentially, this is what we find, where like for the first step, the models do have near perfect accuracy on this very simple task. And this is exactly what we wanted. This shows that the model has the knowledge needed to solve this task. But then one interesting thing we find is that once you scale model size, in one step, there does not seem to be any difference. But then in the number of steps that the model can complete at a certain success rate, you clearly see that scaling model size has like almost like non-diminishing returns, right? It's not like this curve is bending downwards. And obviously, we only have 4 data points here because that's the number of sizes you have for like the Chen-Wen and JAMA models. But essentially, the idea is that um, even though scaling seems to give you diminishing returns in the test loss is sort of like this metric on the per token loss, essentially because you mean or take the average over all the tokens. Whereas once you consider a long horizon task, the length of a task the model can do increases non-diminishingly with scale. And again, like larger models are essentially able to complete larger tasks. And one interesting thing we also found was that like initially, like in Jan LeCun's model, you assume that the step accuracy remains constant, like the error rate at each step remains constant, but we actually found that it degrades. And this is not just because of long context issues. One thing I'm not going to talk about in today's presentation for time reasons, but is in the paper, is we show there's this interesting self-conditioning effect where when models see their own past mistakes, they become more likely to make mistakes, probably because they're trained in this like next token prediction way. And in a context of mistakes, making a mistake becomes more likely. So, and then the other thing you can measure, like this is measuring the number of turns a model can run for. The other thing you can measure is like how long a task can a model execute in a single turn. So we measure this with like the turn complexity. And one thing we found is that even for the largest models, they can't even add like 6 keys without some sort of chain of thought or test time compute, sequential test time compute. So even Kimi K2 like fails to add like 6 keys values and maintain like consistent sums in our task if you don't give it chain of thought. And you can't like emulate like essentially even when you give it parallel compute uh, and not chain of thought, you see that like in this black line shows that its accuracy remains extremely low. But with chain of thought, this gets fixed and like the accuracy increases by quite a bit. And indeed, like when we benchmark frontier models on like the simple task of how many keys can a model add in a single turn, we find that like let's say DeepSeek R1 or DeepSeek V3, they can do like around 120 additions of the keys in our task, whereas Grok 4 and Claude 4 Sonnet are significantly better, like with around 400 steps executed above like a certain accuracy rate. And then one interesting thing was GPT-5 is like way ahead of the pack. And maybe this has something to do with the fact that it was like codenamed Horizon. I think my personal hypothesis is that labs are like extremely focused on long horizon tasks in the last few months. And I think we're starting to see like the benefits of that, where models are like able to complete like significantly longer tasks. So obviously, this is like a very, very simple toy setting, but even in this toy setting, you can see the progress we're making on like longer tasks. And to conclude, essentially, like again, with this sort of work, we basically, even like in the broader community, I think we haven't even scratched the surface of the possible evaluations. Because until now, we've been like so focused on like these knowledge evaluations, which are like these exam style benchmarks, right? Essentially, they're measuring whether you know a fact or you don't know a fact, or you know a certain procedure or you don't know a procedure. So in some sense, like if you think about AGI, the general part of it in terms of knowledge is already solved, right? Like models have extremely general knowledge across domains. No single human can match that. And to some extent, we've also now seen progress on like these algorithmic reasoning tasks, which involve some sort of execution code style reasoning or mathematical like execution and so on. But then there are so many problems out there which we don't even have good evals for. For example, even within reasoning, a lot of reasoning that humans do is like reasoning about uncertainty. Like we want to make a life choice and we don't have complete information, and based on like our partial awareness we want to make like some decision. We can't even predict the future fully, so there's always some uncertainty, and it's unclear how well models do in like these different settings, right? Like again, are models good at reducing their uncertainty by asking good questions? Given like new evidence, are models able to like optimally update their beliefs? uh, in terms of like, again, agentic tasks, we barely have like good multi-agent collaboration evaluations. And then when it comes to intelligence, I think the best we have is like arc agi, which is like, again, like a very small synthetic toy evaluation, which essentially tests how well models can sample efficiently learn new skills. And again, under this tree as well, we basically do not have like great evaluations. We don't have great evaluations for continual learning, for memory, for curiosity, and so on. And broadly, I think for very long, machine learning has been focused on this knowledge paradigm of evaluations. But now that this is getting solved, we really need to rethink how we do evaluations and start evaluating some like these different capabilities which are really important. And one thing which is very interesting is that all of this is essentially a symptom of how broken our evaluations for humans are. Like if you think about how we do like standardized testing, that's exactly how we were testing models. And now that we're realizing that these evaluations are broken for models, just think about how many millions of students' career decisions are made based on these broken evaluations, and what the opportunity is out there for that. And basically the problem is that the real world is complex, and we need to kind of embrace that evaluations, like realistic evaluations, will have noise, but we can still focus on the signal that they provide. And yeah, and finally, like circling back to one of the questions that was raised was, how do we even evaluate models when we don't have a reference answer? Like if they gave like a new scientific idea, how do we know whether it's slop or whether it's like an actual breakthrough? How will we evaluate superhuman capabilities? Because machine learning evaluations have always relied on human ground truth, which we might not have anymore. And these are some of, I think, like the interesting research questions that I'm also myself focused on. Yeah, with that, I'm happy to take any questions. I think I went over time a bit, but sorry about that.
No, this is great. Thank you so much, Shashwat. This is a fantastic talk. We have about 10 minutes left on the meeting, so yeah, feel free to write more questions in the QA format. I also have some questions myself that maybe we can start with. The first,
I'm happy to stay extra. There's no problem on my side for that.
okay, great. Thank
Yeah.
you for that. First one is just more of a technical question, but we talked a little bit at the end about these long horizon tasks. And I noticed that some of the plots had an x-axis for time, others had a number of steps or turns. And so I was curious if there's a common way to normalize on long horizon tasks, because you seem like we could have differing experimental setups with thinking versus non-thinking models, as well as different inference providers based on the time of day. So curious how you've seen that be normalized.
Oh yeah, that's a good question. So I think one interesting design choice we made here was we went for like steps, because we could measure that in a synthetic task, whereas meter went like in the original meter study, which kind of also motivated our work. They went for something which is more the time that it takes a human to perform a task. So the problem with time as an axis, so and then you also have like frontier labs these days talking about how long they ran their model for. Like they say that, oh, Claude can run for like 30 hours nonstop. And I mean, yeah, it's an interesting question where there really is no standard unit, right? It depends on, like, I guess economically it would make sense to use human hours as a metric, because that kind of tells you how much your user will be willing to pay you for your model or your agent. But then at the same time, like the number of steps is a more like you yeah, the number of steps is a more grounded metric in terms of how models perceive it. Because I mean, how do you even count time? Like something that takes me 10 hours might take someone else like 2 hours or 20 hours or 100 hours, and it's like a very subjective metric based on who you're measuring it using. So I do think like the most standard metric would be some sort of steps, but then what is a step depends on the task as well.
Right, exactly. Okay, makes sense. I'll ask one more question. It looks like we're getting some other good ones as well. In the first half of the talk, you talked about evaluating responses and comparing responses with an LLM as judge. And that intuitively makes sense that as we get more complex generation systems, we will have more complex evaluators. We've gone from regex to Blue, Meteor, BERT score, now LLM as judge. And I think we can extrapolate this further and see maybe we have LLM as jury, maybe we have personas. And so I'm curious what the bar is for us to determine whether these approaches are good or bad. Does it mean for every paper where we have a judge, we should have some alignment score with human population? Or what does it take to prove out that these complex evaluators are actually testing what we're looking for?
That's a great question, something that I'm also like actively struggling with every work I do. And I do agree with, so I think obviously the fallback option here is like some sort of human study and you do alignment scores as you mentioned, but then this is like costly depending on how hard your task is. This could be extremely costly if you need like doctors to measure a model's alignment. You probably, like a lot of people won't have access to that. So I do think that this is getting tricky, right? And that's like, I think the hard problem of evaluations now, where to some extent you want to be grounded, but then I don't think there's like a great answer I have for this, but then you can do like some sort of sanity checks on your evaluator. Like you could try different augmentations of the same data, you could try paraphrasing, all sorts of things, see how consistent your evaluator is. But mostly I think in the end it ends up being like some sort of vibe. And it also depends on what your end goal is. If your end goal is to optimize for human preferences, then yeah, maybe measuring alignment with human preference is the best you can do. But if your end goal is like a scientific breakthrough, then you either run the experiment or like get the scientific community's feedback or something.
Got it. Makes sense. Yeah, I think that's a question I probably need to grapple with as well. Okay, actually, want to quickly just hand off to Abby at Vals to talk a little bit about the community we're building, and then we can in the remaining time talk about more open questions that we have. So Abby, you want to say a few words? I think I have to make you unmute.
Yes,
Go
I
ahead.
just unmuted. Hi, everyone. Yes, so we're building a community on alphaXiv where we bring together people to talk about AI evaluations and the best way to determine how well AI can actually perform on all these tasks, and just have a community where, we bring people together to talk about this. So I'm going to send a link in the chat. Would love for you guys all to join and keep the conversation going there after this call. And we'll be having more discussions like this moving forward. Our next one is with Mike Merrill at the same time next week, and I'll also be sure to share the Luma invite for that as well. So thank you guys all for coming, and thank you, Shashwat, for such a fantastic set of slides and presentation. It's awesome.